Chapter 8 concerns itself with confidence intervals, and these are intervals that help us to estimate what the mean and the proportion of a population actually are. Let's cover some definitions that you're going to need in this chapter first. And the first one is the value assigned to a population parameter. Now, if it's based on a sample statistic, we call this value an estimate. Now, the value that a sample statistic has that's used to estimate a population parameter is called a point estimate. We're going to be doing something called interval estimation. Now, this is an interval. It's a set area which is constructed around the point estimate. And it is stated that this interval contains the corresponding population parameter, and we'll be giving it a certain confidence level, a certain degree of confidence. In other words, we'll be saying that the population parameter is probably within two numbers, and we'll be giving a level of confidence. How confident are we that that number exists within those two numbers inside the interval? Now, the number we add to and subtract from the point estimate in order to get this interval is called the margin of error, or it could be called the maximum error of the estimate. Now, once again, we're going to be illustrating confidence intervals by drawing them on something that looks a lot like the standard normal curve. In interval estimation, we say an interval is constructed around the center, and the center is always the point estimate. And we state that the interval is likely to contain a corresponding population parameter. So if we're estimating the mean, for example, we say that the population mean is probably within this confidence interval that we're going to set up. In this page, in this slide, I've illustrated it with the numbers 395 and 405. Those would be the 2 points that we're at the limits or the boundaries of our confidence interval. And we're stating that we believe the population mean, the actual population mean, is within those two numbers. The question is, how confident are we that the population mean is within our confidence interval? Well, to illustrate this, we say each interval is constructed with a given confidence level. So that's why they're called a confidence interval. Now, the confidence interval always is centered around the point estimate. It is, in fact, the point estimate plus and minus the margin of error. So, for example, if we have a mean or an average test score on test 3, it was 80, and there was a margin of error of 2.5, well, the confidence interval would be 80 plus or minus 2.5, which would actually give it an interval from 77.5 to 82.5. And in interval notation, of course, that is a parentheses, the lower limit, which is 77.5, comma, and the upper limit, 82.5, and close parentheses. So let's talk a minute about this confidence level. As I told you before, a confidence interval is always constructed with a specific confidence level in mind. This level says how much confidence we have that the interval that we form or we create contains the true population parameter. So a confidence interval provides a range of reasonable values, and we expect the population parameter to fall within this range, but there's no guarantee. There's no guarantee that any single confidence interval will have or will contain this unknown population parameter. For example, if we don't know the population mean, and we won't, that's why we're setting up the confidence interval, we have no guarantee that the interval we set up will contain it. We only have a certain probability that it is contained. So we're going to use something called alpha. Alpha is going to be defined or described to us as the area that's under the curve outside the confidence interval, which should contain the parameter we're researching. Now, to find the probability that our population parameter is within the bounds of the confidence interval, we must find the actual areas involved. And again, we use Z to find these areas. As you can see in this illustration, what I've done is taken alpha, whatever, and it is associated with our confidence level, alpha is, and divided it into two pieces and put those in equal pieces in each tail. So alpha divided by 2 is in each tail of the curve, and the inside of it, where is really our confidence interval, we're pretty certain our mean resides within that, our population parameter, is really 1 minus alpha. Now, the confidence level will help us determine how big alpha and alpha divided by 2 actually are. In other words, how big are these areas that are in the tail, and that'll help us determine what those z-scores are. Now, different research methods use, or different research areas use, different levels of confidence. For instance, if you're dealing in education, a 90 or 95% level of confidence is quite common. But if you were dealing in medicine, any kind of medical research, that's not quite good enough. So you're going to be reaching for higher understanding or using higher confidence levels, such as 99% or even 99.9%. The most common confidence levels that are used are 90%, 95%, and 99%. So what happens is we take, for instance, a 90% confidence level, and we say, okay, that area in the middle that we think the population parameter resides is really equal to 1 minus alpha, or 0.9% of the curve. So alpha is the rest of it. Alpha is 0.1. Now, I have to do alpha divided by 2, don't I? Because I'm splitting it up for confidence intervals. I always divide alpha and put half of it in each tail. So what you'll do is draw a curve and label. You'll label 1 minus alpha, and you'll divide alpha into 2 pieces and put half of it in each tail. And then you'll be able to find the corresponding z-values, and you'll use the standard normal tables to do this, the z-table. There are some basic scenarios for finding confidence intervals, and these are listed here for you on this page so you can sort of tell what we're going to do, but we're only going to use one of them to start with. First of all, you check and see, is your confidence interval for the mean or is it for the proportion? Now, if it's for the proportion, your decision is already made. You'll always use the z-table for it. If it is for the mean, though, you have to know if you are given the population standard deviation or not. Now, if you're given the population standard deviation, then you use the z-table. But if not, you're going to use a new table, something called the t-table. And we'll go into some examples of that in just a minute. Before we go into anything else, let's take a look at how to determine what the z-score is that we need with the different confidence levels. And we'll use these 3 most commonly used confidence levels that I told you about. Let's start with the 90% confidence level. If we are 90% sure, we want to be 90% sure that the estimate that we make, the confidence interval that we set up, has the population mean within it. First, we're going to set it up and say, okay, my 90% is equal to 0.9. Alpha is going to equal 1 minus that 0.9, right? So it's going to be 0.1 or 0.10. You can I'll write it down here for you. It's 1 minus the 0.9 is how I got that. And then I have to divide alpha in 2. Now for confidence levels, I will always divide alpha in 2 pieces. And for this one, I'll get 0.05. What this means is I then go to my z normal curve. I'm going to set it up. And I'm going to do like I always do. I'm going to set it up with the center of it being 0. And I'm going to go over here and illustrate that I'm going to be putting in each tail of the curve alpha divided by 2. This area is 0.05. This area is also 0.05. And this center part, just so you'll know what I've done here, this center part contains the rest of it, 0.9. That's where I expect my confidence, I'm 90% sure that my population mean is going to reside within these 2 points that I'm going to determine later. But what I've got to find out first is, what's the z-score? That's my first step. So I go to my z-table and I look it up. Now, in these confidence levels or confidence intervals, you're never going to need the positive side of your z-table. You can look up everything on the negative side because the positive side is just exactly the opposite. And I'll show you what I mean. What I want first to find here is an area of 0.05. Now that's 0.0500 if you want to add the other 2 digits, because the z-table has 4 digits. 0.05 is really close to, right here, I think I can see it, is really close to negative 1.6, and it's either 1.64 or 1.65, and generally, I just happen to know what I use for this one. I usually use 1.65 for the 90% level. So I would say this number right here is a negative 1.65. So the other side of this is going to be a positive 1.65. So I have found my z-scores, 1.65, and when I set them up, it was plus and minus, wasn't it? Now let's go ahead and see what the next question is that we're asked. You can go ahead and explain this. What it means is we are 90% sure that the population mean is going to be between a z of a negative 1.65 and z of positive 1.65. And that's really setting up a 90% confidence interval. Okay, so let's look at the next one and see what we can do for a 95% confidence level. First, we would say, okay, alpha is, once again, I'm going to say alpha, if I want 95% in the middle, I'm going to have to take 1 minus 0.95 and find alpha. And that only gives me 0.05 to work with. So when I divide 0.05 by 2, I come up with 0.025. So once again, let's draw this and put this area in the tail. Here's 0. And the areas in the tail have to represent 0.025. That's the area. So you could add a 0 if you want to look it up, if it's easier for you on the z-table. Once again, just go to the negative side. It's easier. Find 0.025. You should be able to find it exactly. This one is right here. It exists. It's negative 1.96. So the z-score, negative 1.96, goes here, and the positive 1.96 goes here. My z's that I'm working with are plus and minus 1.96. That's going to be my confidence interval. Now, I'm going to be 95% sure that my population mean is going to reside within those two z-scores when I set up the rest of my parameters, okay? Okay, the final one you should be able to do by yourself. Go ahead and try it, and then come back and check your work. So I'm dealing with 99%. I'll say 1 minus 0.99, and I have a very small area to work with, 0.01. And when I divide that by 2, I get 0.005. Well, let's see if I can draw this and put 0.005 in each tail of my curve. And then go to the z-table and look it up. 0.005, if you need another decimal, it's a 0, right? 0.005, it's really small. It's hard to find because we have a tendency to go 0.05. It's not, it's 0.005. And it's really between these two numbers. And we generally use this one, so I'm going to go with negative 2.58. You could have done either one and you would have been fine. So this is a negative 2.58 and a positive 2.58. And the z's we would use are plus or minus 2.58. Now those are your 3 most common confidence levels, and those are the z-scores associated with them. Now sometimes it's easier because you'll work a lot of problems and they'll have these 3 confidence levels. If you memorized these 3 z-scores, it would be a little easier for you. However, you may come up with a confidence level that's totally different, 97%, 92%, and you'll have to go through this process again. Make sure you mark this page so you know where it is. Go through this process again and figure out what the z-scores are for those different confidence levels. Now, as I was telling you before, when I got a little ahead of myself, we have these 3 basic scenarios for setting up confidence intervals, and we use this chart to figure out which table you use, because now we're going to add today something called a t-table to the tables that you're going to use, and you'll find it at the beginning of Module 4. So you want to remove that one. On Test 4, you'll be using both the z-table and the t-table, so we need to learn how to use that one. So what we have to determine first of all is this a confidence interval for a mean or a proportion? Proportions always use the z-table, as I told you before, but the mean, you have a question you have to answer. If it's the population mean that you're trying to estimate or find the confidence interval for, you've got do you know the population standard deviation? If you do, you can use the z-table, but if you don't, what you're going to have is the sample standard deviation, and you'll be using the t-table because of it. Now, the actual boundaries of a confidence interval for the mean are set up by putting the point estimate of the sample mean. The point estimate is the center of our confidence interval, and we'll use the sample mean as that point estimate. And then you will add and subtract from it something called the margin of error, or the maximum error of the estimate. Now, the way we get that is we take our z-score and we multiply it times our adjusted standard deviation. The standard deviation in this case always has to be adjusted by taking the population standard deviation and dividing it by the square root of the sample size, which is something we're familiar with doing. So let's take an example and walk through it together on page 4. It says that there's a sample of size n is equal to 42, and then the mean price of the book, the sample from that mean, is $125. So we don't know the actual population mean, but we do know the sample mean. The population standard deviation is given to us, though. It's known to be $31. So we want a point estimate for the mean of the population. In other words, we want to estimate where the actual population mean price of this book is, within what two numbers, how close to the sample mean that we took is it. So we are willing to be in error. We want 95%. We want to be 95% confidence that we get it right. So we're going to set up a 95% confidence interval, and then we're going to have to calculate our margin of error and set up this confidence interval. First of all, let's talk about the mean. We're going to use, as our estimate for the population mean, we're going to use the sample mean. That's going to be our point estimate. So we will use a sample mean of 125. Now, once again, this is the point estimate. This is what we're going to be building our confidence interval around. Now, for a 95% confidence interval, you can go back to that previous page that you did and say, I've already done that one. For that one, a z is equal to 1.96. Now, for these calculations, you're only going to use the positive side of the z-score. You just ignore the fact that we have a negative on one side and positive on the other. Just use the positive to do our calculations, okay? Next, let's find that standard deviation that we need. We take the population standard deviation, which is known to be 31, and we divide it by the square root of our sample size, and we have a sample of size of 42. When I do this, I get a standard deviation of 4.7834. Now, let's find the margin of error. Now, this is the margin of error that's going to help us determine how much we're willing to miss it by, okay? So for this margin of error, we have a formula that we've given. The margin of error is equal to the z-score times that standard deviation we calculated. So I'm going to say this is equal to 1.96 times my standard deviation of 4.7834. So my margin of error for this problem is going to be 9.38. How do I set up my confidence interval? Well, it's centered around the point estimate. The point estimate is always the sample mean. And so I'm going to say it's going to be my sample mean plus and minus that margin of error, 9.38. So when I set this up, I'm going to have the lowest value it can be. It's going to be 125 minus 9.38. When I do that, I get 115.62. And the highest number it can be is 125 plus 9.38, which will be 134.38. So this means that I can be 95% sure that the population mean price of the book is going to be between $115.62, this is dollars, and $134.38. If you're developing a textbook, writing a book, and you want to know where the population, what the price of the books is generally considered a fair price or an average price, this might be one way you would go about setting up the problem. Now let's continue, because you're going to have a lot of problems like this, and they're going to be word problems. They're going to be real life scenarios, and this is part A of our exercise. It says the nursing department needs to create an information brochure for students interested in a nursing career. The average salary of a nurse on the Treasure Coast needs to be included in the brochure, but it's not very practical to contact every nurse on the Treasure Coast and ask for their salary. So we're going to compute the true population average salary, okay? We're going to try to estimate it, so we can't ask them for it and then make a real population average. So instead, the nursing department contacts a random sample, and there's my sample size. They're going to contact 36 nurses, ask for their salary, and comes up with a sample mean. Now the sample mean for those 36 nurses is $56,000, okay? That was my sample average, sample mean. Now, since the sample data did not include every nurse on the Treasure Coast, the population mean is most likely not exactly 56,000, but we're hoping it's close. So it's appropriate to fix a confidence interval, and we'll center it around the point estimate of our population mean, which is $56,000. And we're going to get a range of likely values for the average salary of all nurses on the Treasure Coast. Now suppose the standard deviation of all, and it says all, so this is a population standard deviation. Standard deviation of all nurses on the Treasure Coast is $6,000. And the nursing department wants to use, now they want to be really certain they get the right population mean inside their numbers they put in this brochure, so they want to use a 99% confidence level. Okay, so we've got to answer some questions. What is the point estimate of the mean salary for all Treasure Coast nurses? Okay, now the point estimate is always going to be the sample mean. Okay, the sample mean is going to be the point estimate for us, so that's it. And then we want to determine the margin of error for a 99% confidence interval and construct a 99% confidence interval for the mean salary of all Treasure Coast nurses. So you ask yourself first, 99% confidence interval, alpha gets split into two pieces, put on each side, go back to page 3, and see how we do it. But that 99% confidence interval, we know what a z-score has to be. We determined it to be 2.58, remember? Because I took how did I find it? I took alpha and divided it by 2 and came up and compared it to the areas of the z-table and came up with my z-score. Now, I want to find the standard deviation of x bar. Remember, I have to take my standard deviation. I was given the population standard deviation. But to use it, I'm going to have to divide it by the square root of the sample size, and I have a sample size of 36. So really, what happens is this is 6,000 divided by 6, right? So my standard deviation, my adjusted standard deviation, is going to be 1,000. Now how do I do my margin of error here? Well, I take my z-score, and you have this in your formula sheet, so you don't ever have to wonder what the formulas are. Go back and make sure you can find them, and multiply that z-score times my standard deviation that I just adjusted, and I come up with a margin of error of 2580. So here's my confidence interval. It's going to center around my point estimate, which is the population mean. So I take that sample mean, sorry. I take the sample mean, where's the sample I took, and this is the sample mean that I got. So I take that sample mean of 56,000, and I say plus or minus that margin of error. I'm going to miss it by this much either way. I'm going to build myself a confidence interval there. And when I do this, I come up with some numbers. I'm going to write them down here. The lower number would be 56,000 minus 2580, which is 53,420. And 56,000 plus 2580, which is going to give me 58,580. And read the sentence that we've just filled in. What this means is we can be 99% sure that the population mean salary of all Treasure Coast nurses will be between these two numbers, and it's based on the sample that we took and based on the confidence interval that we created. Now let's kind of look at part B here. For part B, we're going to look at the previous exercise to get some information. And we're going to suppose this time the nursing department decided instead of a 95% confidence interval, instead of a 99%, they want to construct a 95%. So they're going to do, instead of 99%, we have to change our z-score, don't we? We have to go back and see what the z is for 95%, or we have to calculate it again. And then create and set up the confidence interval. And you're going to have the same, please note, you're going to have the same you're going to have the same point estimate. Your sample mean has not changed. Go ahead and see if you can complete this one and then start to check your work. All right, recall that for a 95% confidence interval, when we did this one before and we found it on page 3, I can go back and show it to you, we looked at our alpha divided by 2 of 0.025. Remember, we split alpha into 2 pieces. Looked that up in our z-table and found the z-score to be 1.96. We're going to use the positive 1.96 to calculate our margin of error. So what is that standard deviation? Well, we have a different sample size. If we don't have a different sample size, it's exactly the same thing that it was, and sample size hasn't changed. All that's changed is we're changing our confidence interval. We're changing how confident we want to be. Instead of 99%, we're going to be a little more lax and say we can just be 95% sure. So the margin of error is going to be this new z-score, 1.96, and it's going to be multiplied times the adjusted standard deviation of 1,000. So I'm going to end up with 1960. And when I create my confidence interval here, I start with that same point estimate, which was 56,000, the sample mean, and I'm going to add and subtract this time the margin of error of 1960. Well, 56,000 minus 1960 is 5440, and 56,000 plus 1960 is 57,960. So this time I have a broader range that I'm looking at. I'm looking at from 54,000 to 57,960. I'm only 95% sure instead of 99% sure that my population mean falls within these numbers. So let's take another scenario with our nursing department and our nursing salaries example. And let's say that the nursing department decided the original margin of error was just too large, but they don't want to go down on their confidence level. So instead, they decide to increase their sample size from the original 36. They're going to go up to 100. They're going to sample 100 people. Now, we're going to presume the average of this new sample of 100 nurses gives the same average salary. Okay, we're still going to work with the sample mean being 56,000. And if everything else remains unchanged except the sample size, let's look at what difference this makes to our confidence interval. So for a 99% confidence interval, once again, we use that z-score that we calculated before, 2.58, and we take the standard deviation. We're going to keep it the same too, taking 6,000, and this time though we're dividing by the square root of 100, so it's going to be 6,000 divided by 10 instead of 6,000 divided by 6. This is going to give us a smaller standard deviation, isn't it? It's going to give us a standard deviation that we're working with of only 600. So what's our margin of error going to be? Well, we take 2.58 and we multiply it this time times 600, and we come up with 1548. Now that margin of error, when it's added and subtracted with the point estimate, the sample mean, is going to give us the lower limit, or the lower part of our confidence interval, is 54,452, and the higher number is going to be 57,548. That's supposed to be a comma there. So how exactly did this affect us? Well, this part that I put in bold here is really important. What this demonstrates is that if the level of confidence is directly related to the margin of error, and it is, then if we do two confidence intervals with different levels of confidence and we construct them from the same sample data, then the confidence interval with the and that should be lower level of confidence, will have the smaller margin of error. In general, a lower margin of error is desirable, but arbitrarily lowering the level of confidence is not recommended. So there's usually a better way to decrease the margin of error, which we'll discuss in a minute. So before you go on, be sure you go back over these examples of the nursing department salaries brochure that they're trying to create, and make sure you understand how these margins of error are affected and what the different manipulations of the confidence levels are doing to the data. And then move into this discussion with me, which is the width of the confidence interval. The width of the confidence interval, it really depends on the size of what? Well, it depends on the size of that margin of error, doesn't it? And of course, that's what we say, we abbreviate as E. And that, the margin of error, depends on the z-score, the population standard deviation, and the sample size. Now, I've written this down for you so you'll understand where I'm coming from. Those are the two formulas we've used to calculate it. But look at this. The value of that population standard deviation is not under the control of the investigator. As a researcher, you have no control over what the standard deviation of the population is. That's just something that goes with the data. It happens to exist. So how are you going to adjust this width of the confidence interval if you want to? Well, the value of z, that's something, but that depends on the confidence level. Okay, what if we don't want to change our level of confidence? Then the only thing left is the sample size. Now, the confidence interval, when the standard deviation of the population is known, of course, you want to write these down one more time just to make sure you've got them, is point estimate plus and minus the z-score times the population standard deviation of x bar. Okay, standard deviation of x bar, the one we adjusted. And of course, this right here is what we call the margin of error. Now, how does that kind of compute? Well, x bar is really equal to, plus or minus, sorry, x bar plus or minus the z-score times, and how do we get this one? Well, we say population standard deviation divided by square root of the sample size. And when you're looking at this, you can tell the only thing you really got control over here, if you don't want to play around with your z-score and change the level of confidence, you're going to have to adjust the sample size. Now I left you one more place to write out these formulas. Margin of error is equal to z times the standard deviation of x bar, which is equal to z times the standard deviation of the population divided by the square root of n. You get the picture. I'm having you write them enough times that you can memorize them. Now here's an activity to complete on your own, but I am going to help you with the first one and then let you do the second one alone. This says a publishing company has just published a new college textbook. Before the company decides the price to sell the textbook, it wants to know the average price of all textbooks in the market. So the research department of the company takes a sample of 25 comparable textbooks and collects information on their prices. This information gives us a mean price, and notice this is going to be a sample mean because they took a sample of 25. So there's a mean price of $145 for the sample. It's known the standard deviation of the prices of all, so we do know the population standard deviation is right here, isn't it? I'll put that symbol under it so we know it's $35, and the population of such prices is normal. So now I have given you a good bit of information for you to set up your confidence interval, and you should be able to follow along with what we've done here and create your confidence interval. You're using a 90% confidence interval for part B, and you can go through and write down what we did. Go back to page 3 if you have any questions, but try to do it without page 3 and get your z-score so that you'll be familiar with it in case you have to break away and do some odd confidence level like 97. And then go ahead and complete that page, and you can check back with me later on the answers. Now, like we said before, that sample size is extremely important to us because it might be one of our only ways of making an adjustment is using that sample size. So how do we determine a sample size for estimating the mean? Well, given the confidence level, which gives us our z-score, and the standard deviation of the population, then we can set up a formula and we can calculate the sample size that will give us a predetermined margin of error. So we get to decide what the margin of error is that we're interested in or that we're happy with, and then we know the confidence level that we want, so we know our z-score. We already know the standard deviation of the population. We have to know that. And then we can use this formula, z-squared times standard deviation squared divided by margin of error squared, to come up with our sample size. Now, if it's a proportion problem, I'm going to go ahead and tell you we change it a little bit. Instead of the standard deviation, we use P times Q. Everything else really remains the same. So let's look at an example that really tells us how this affects our sample size and what the margin of error that we choose, how that affects our sample size, because that's one of the things we can actually manipulate. And we're going back to the nursing department. They haven't collected any data for their confidence interval of average nursing salaries, and they want to figure out what sample size they need to produce a confidence level, and they want their maximum margin of error to be $1,000, okay? If the confidence level they want is 99%, and they know the population standard deviation is 6,000, there's nothing that can be done to change that. So let's write all those things down. We know the population standard deviation. We've decided that we want a margin of error of $1,000. That's as much as we want to go. And we know a 99% confidence level is what we want. So we know the z for that is 2.58. Okay, so let's plug all this in. We've got z, which is 2.58 squared, times the population standard deviation of $6,000 squared, and then we want to say our margin of error is 1,000 squared. So you plug all that into your calculator, and it should work fine because order of operations should work with you on this one. And what you'll come up with is 239.63 whatever. Okay, the point is we are surveying people, and there's no such thing as 0.6 of a person. So no matter what this decimal is, we have to go up to the next whole number. In other words, if this had come out to be 239.3, you'd still have to go up, and you would use a sample size of 240. So it's not rounding up, it's just bumping it up to the next number. Let's take this a little bit further. We're looking at this same example, and we want to know this time what sample size is going to be required if the nursing department's decided they want their estimate for the mean to be within $100 of the true mean salary. Okay, they said, okay, we can miss it by $1,000 and we're okay. But now they're going, maybe we don't want to miss it by $1,000. Let's just see if we can miss it by $100. We'll see how that changes your sample size. Go ahead and do the calculations and see how many you would need to survey if you're going to change and lower your margin of error down to $100. Hopefully you've done this. I'm starting out with the same information except for my margin of error is 100. I still have everything else the same. And this is, once again, 99% confidence interval. None of that changed. Okay, the only thing I changed was the margin of error. So I'm coming over here with my z of 2.58, my population standard deviation of 6,000, but down here I'm going to divide by 100 squared instead of 1,000 squared. And when I do that, you probably got a shock at how many people you really needed to survey. And like I said, we still have to bump this up because it's not 23,963. It is, you have to have one more person because you have to have at least this many, and there's no such thing as 0.04 of a person. So I've got 23,964 is how many people I would need to survey. Looking at this, I would say the nursing department would probably go back and decide that missing it by $1,000 is probably okay. because there's a big difference in getting 240 people to complete a survey and getting 23,964 people to complete a survey. So what conclusions can we draw? And this is an important paragraph I've put for you at the bottom. To shrink the margin of error without decreasing the confidence level, you can increase the sample size. So as this sample size increases, what happens? Well, as the sample size increases, the width of the confidence level, actually, or the confidence interval, decreases. This gives us a more accurate estimate without decreasing the confidence level. Otherwise, the only way to shrink the width of the confidence interval is to decrease the level of confidence that you want. You know, that gives us the z-score. And it's not always advantageous to shrink your level of confidence. So let's talk about that new table that we're going to start using in this chapter. It's the t-table, or the t-distribution. The reason the t-distribution came into being was because we didn't know how to calculate a confidence interval when the population standard deviation was not known. Now, this question was actually put forth and answered by a man named William Gossett in 1908. He published it under the pseudonym Student. And the reason he did that was because he worked for Guinness as a chief brewer, and they didn't want people to know that they were using statistics. They thought that was a trade secret. So he couldn't really say what he was doing, and he had to publish under a pseudonym. So this became known as Student's t-distribution. Now, it's actually a family of distributions. It takes into account the sampling error of the standard deviation for relatively small sample sizes. Now, the reason this is necessary is that for small sample sizes, the difference between the population and the sample standard deviations are more pronounced, and that leads to greater variability in the sampling distributions for a small sample size. So find your t-table or your t-distribution at the first of Module 4, and be prepared to be watching that and looking at it, because we're going to use it to look some things up. But I want to say that really what it's for is for samples where the population is approximately normally distributed and the population standard deviation is not known. That's when we can use the t-distribution. It is still a specific type of bell-shaped distribution, but it does have a lower height. It has a greater spread than our standard normal distribution that we use in the z-table. However, as the sample size becomes larger, the t-table, the t-distribution, approaches that standard normal distribution, the one we've been using with the z-table. So we can actually use it as we get larger and larger sample size. We can actually go to the z-table. Now, the t-distribution only has one parameter. It's something new that we haven't talked about before. It's called degrees of freedom, and we abbreviate it DF. For our purposes in this class, we're going to calculate the degrees of freedom as the sample size minus 1. So it's really going to be simple. Now, as I said before, as that n approaches, the sample size approaches infinity, well, the t-distributions can't be really told very easily. It's practically indistinguishable from the z-distribution. In fact, we're going to use the t-distribution in this class. It only goes up to degrees of freedom 75. That's a sample size of 76. And at that point, the t and the z distributions are basically the same. But you could use the z distribution if you wanted to, if your sample size goes higher than that, or you could just use that last row of the t-table, which is going to say degrees of freedom infinity. So how do we use the t-distribution to create a confidence interval for the mean? Well, it's really very similar to what we've been doing, except this time, instead of z, we just have the t-table, the t-score instead of the z-score. So the confidence interval for the mean would be the sample mean plus and minus what we call the margin of error, and that's going to be the t-score times, and this is a little bit different, but it's the sample standard deviation, and it's the sample standard deviation of x bar, which has to be adjusted. We'll take the sample standard deviation and divide it by the square root of n. Basically, if you look at this, you're doing the same thing. However, you do not have the population standard deviation to deal with. That's the basic reason we're going to the t-table instead of the z-table. Since I don't have the population standard deviation, I use S to represent the standard deviation of the sample that I have, and I divide it by the square root of n to get my sample standard deviation of the sample mean, sample standard deviation of S of x bar. Now, the value of t that we get from the t distribution table for the degrees of freedom that we're working on will be used given, and we'll also use the given confidence level. So that's your margin of error, t times the standard deviation of x bar, which we had to calculate like we did before. And the confidence interval is still going to be the sample mean plus and minus the margin of error. We just calculated the margin of error differently. Now, I've put a section of the t-table here on this slide so we can discuss it. One thing I do want you to note is where the z-table is really measuring area to the left of the z-score, the t-table is doing the opposite. It's giving us the area to the right of a t-score. So that's a little bit different and confusing. The other thing is you're dealing with the sample size explicitly -1, which is called the degrees of freedom. So if we want to find a t-value for 14 degrees of freedom, that means our sample size was 15, n was equal to 15. We're dealing with 14 degrees of freedom. The first thing you do is find that row for degrees of freedom. And here it is on this chart on the slide. And this row with these 6 numbers is the only row you are allowed to use for that problem. So there's the rows. That's the row I have for this problem because it's really strictly based on your sample size, which gives you your degrees of freedom. And then we want to find the t-value for 14 degrees of freedom and 0.05 in the tail. So what is the t-score? Well, 14 degrees of freedom, it has to be one of these. The t-scores are not on the outside anymore like they are on the z-table. They're on the inside. The area, alpha, or alpha divided by 2, or whatever, that alpha is in this top row up here. Now, this is given something called a two-tailed test and a one-tailed test, and what we're really looking at here is when we're doing confidence intervals, we always have to divide alpha by 2 and put it in each tail of the test. So we'd be dealing with an alpha of 0.05 over here is what we'd be dealing with. But in this illustration I've given you, it's really just depicted a one-tailed test where all of alpha is sitting right here in one tail, and that area is 0.05. So let's pretend that this is my 0.05 area. I go down to degrees of freedom 14, and I find my t-score, 1.7613. Now my z-table didn't have that many decimal places. That's another difference in the t-table and the z-table. So let's take a look at this student's t-distribution table just a second, and I want to point out a couple of things. This particular table gives you an alpha level for a one-tailed test and a two-tailed test. I'm probably going to only use this row, the one-tailed test. I'm not going to look at the two-tailed test because we're going to know whether we're splitting alpha in two pieces or not, and this two-tailed test thing assumes that you really don't know, okay? And it also gives you those confidence interval percentages, and that might help you later on. But basically, we're kind of going to base it on this bottom row here, this bottom header of one-tailed test. Now, degrees of freedom go all the way down the side, and you're going to note there's no positive and negative side to this table. Once we get past 75, we hit infinity, and you can use that, or after you get past 75, you really could use the z-table because it does approximate it very closely then. Inside, as I told you, inside this t-table, we have the t-scores. Outside is the areas, and over here is the first thing you have to identify, which is the degrees of freedom, n-1. After you find the degrees of freedom, the only row you're allowed to use is this one single row that identifies with the sample size -1. So let's take our t-table and construct a confidence interval for the population mean when we do not know the population standard deviation. That's the key to knowing if you're using the z-table or the t-table. This is going to be population standard deviation not known, so we're going to be doing our new table for it. We have a sample size of 25, we have a sample mean of 186, and we have a sample standard deviation. I know because they used S. Given to me, and it's 12, and the level of confidence I desire is 95%. So I want to do a confidence interval, and the first thing I'm going to do is come down here, and I still need to divide my standard deviation by the square root of the sample size, even if it's a sample standard deviation. So I'll come down and do that first, and I end up with 2.4. That calculation out of the way. Next thing I'm going to do is find what my t-score is going to be for this one. Now, I've got an n is equal to 25. So what's degrees of freedom? It's going to be n minus 1 or 24. So I've got a degrees of freedom of 24. Now, I also need to find each area. What's the area in the tail? Now, I've got an alpha level given to me. Now, we're going to do this the same way that we did z, so that it'll make sense to you and I won't be changing anything on you. So I've got an alpha of 1 minus 0.95, don't I? So it's going to be 0.05. And for confidence intervals, I always divide by 2. So this is going to be 0.025. Now, from the t-table, what do I find first? The first thing I find is where are my 24 degrees of freedom. 24 degrees of freedom, and then I want to go to the top and look for an area of 0.025. So here's 24 degrees of freedom. It's on the first one. 24 degrees of freedom. My t-score is somewhere on this row, but I won't know until I go to the top and find, and I'm going to only use, like I told you, the one-tailed test, even because it's been split. And it is 0.025. Here it is. And that's going to come down to be 2.0639, right? 2.0639. I could say 2.064. Most people do, but let's do a t-score of 2.0639. So what is the margin of error here? Well, the margin of error is that t-score, 2.0639, times the standard deviation that I adjusted. And I will come up with a margin of error of 4.9534. I believe that's what it is. I rounded to 4 decimal places. So here I have it. My sample mean is still what I'm going to build my point estimate around. It's going to be my sample mean, which is 186, and I'm going to add and subtract 4.9534, and I'll come up with my confidence interval. Now I'm going to round these to 2 decimal places because I didn't give myself much room, but I say 186 minus, let's say, 4.95, shall we? It comes up to be 181.05. And I say 186 plus 4.95, and I get 190.95. And let's take a look at what this looks like if I put it on the curve, because you need to kind of see what's happening, what we're doing. So what I have here is I have a t-score instead of a z-score. And underneath, I'm dealing with sample means, because that's the data I've been given. T-score in the center is always still 0. The sample mean, the point estimate, is 186. That's what it's going to be, the point estimate that I'm building my confidence interval around. When I came over here, I said, well, alpha divided by 2, didn't I? I split it and put it in both sides of the curve, and the area I put there was 0.025, because alpha itself would be 0.05. And then when I found the t-score, I found it to be a negative 2.0639 and a positive 2.0639. And feel free to round these to 3 decimal places if you want to. I'm probably going to do that in the future. And then when I built my margin of error, I found the sample means that I'm working around, and it came out to be 181.05 and 190.95. So what is this telling me? It's telling me that I am 95% certain that the true population mean is between these two numbers, 181.05 and 190.05, built around the point estimate of 186, the sample mean. Now, I want you to do one on your own. Come up with a 99% confidence interval for the same data. So 99% confidence interval for this is going to mean, I'll help you with this, that alpha is going to equal 1 minus 0.99 or 0.01, isn't it? And then it's saying alpha divided by 2 is 0.005. So how you're going to look up the t-scores, you're going to use this area, and you're going to use the same degrees of freedom because it hasn't changed. The sample size hasn't changed. And you should be able to come up with your confidence interval, and you should be able to draw and label your curve. So I didn't want to leave you on your own completely with this one without giving you an answer since we just started t-tables. Let me walk you through it. Hopefully you have tried it on your own. Let's say that we've got the same degrees of freedom, 24. So that's the only row that we can look at is row 24. And I go down here to degrees of freedom 24, and this time I'm dealing with the area of 0.005. So my t-score is 2.7969. Now, like I told you, feel free to go 2.797 if you want to. 2.7969. And then I'm going to calculate my margin of error, 2.7969, and it's going to be times the 2.4. The standard deviation didn't change because the data really didn't change. And that's going to give me a margin of error of 7.7126. I'm going to round that to 2 decimal places and use 6.71 as my margin of error. I'll add and subtract that from the point estimate, and my point estimate stayed the same, didn't it? What was the point estimate for this one? Well, let's do it like this. These are t-scores. This is the sample mean, which the point estimate was 186. And this time, the area that I've got in each side of the curve is 0.005. Much smaller, isn't it? So my t-score came out to be a negative 2.7969. And this one is a positive 2.7969. And then underneath that, I'm going to say, okay, I'm going to take the point estimate of 186, subtract the margin of error, 6.71. I come up with 179.29. That matches up with that negative t-score, doesn't it? And then I take my point estimate of 186 and add the margin of error, and I get 192.71. That matches up with the positive t-score. So this is basically what it should look like with your confidence interval of 99%. On page 11, I have some more exercises for you, and really you should try to complete page 11 completely on your own because there's nothing new that I haven't taught you, and then come back and check your work. First, let's see if we can determine the information that's in the blanks here. I want to see if this told me my sample mean, my sample size, which I can get my degrees of freedom, my sample standard deviation, where I can calculate my standard deviation of x bar, and then I need alpha so I can divide it by 2, come up with my t-score, so on and so on, right? Just like we've been doing. So AAA published the average daily gas price for the entire nation as well as individual states, and to estimate the average gas price in Florida, AAA contacted a random sample, there's my sample, random sample of 50 stations around the state. So I'm going to go ahead and say that sample is 50. And they found that the average gas price for those 50 stations was $2.46. That's the sample mean, isn't it? And there's a standard deviation, sample standard deviation, right? Because it was taken from the sample of 15 cents. I'll say 0.15. Now, 50. So the degrees of freedom has to be 1 less, it's 49. And from there on, I can go forward and create my curve and create my confidence interval, can't I? First, I'll do this standard deviation calculation. I'll take the 0.15 and adjust it by dividing it by the square root of that sample size of 50. And I'm going to come up with 0.0212. And then I'm going to say, what confidence level do they want? Well, they want a confidence interval of 99%, gives me an alpha of 0.01. And if I divide alpha in 2, I get 0.005. And I can look up my t-score now because I have that alpha divided by 2, and I have the degrees of freedom, don't I? So I'm going to look at 49, which takes me to my second page of the t-table, 49. And I'm going to go over here to, I'm still using this bottom one-tailed test column. And I'm going to go down here to 2.68. There it is, 2.68. So t-score 2.6800, but I really don't need that part. And then I'm going to calculate my margin of error. It is the t-score of 2.68 times that standard deviation of 0.0212, and I end up with 0.0568. I'm going to use, because this is gas prices, I'm going to go up to 0.06 and use that. Now I'm going to take my point estimate. What was my point estimate? Well, it was 246. And I'm going to subtract 6 cents from it and add 6 cents to it and get 240 for the lower number and 252 for the upper number. How does that look on the curve? Well, here's the t-score and here is the sample mean, and the average price was 246. And I come over here and I set my alpha divided by 2 areas. How big are they? 0.005. I used that to find the t-score, well, plus the degrees of freedom, right? And I found those t-scores to be 2.68, so this is the negative 2.68, and this is the positive 2.68. And then when I set up and said I found my margin of error and subtracted it from my point estimate, I came up with 240 for this sample mean, and over here I came up with $2.52 for that sample mean. So data values, sample means, t-scores, and this is my confidence interval that I've created. So let's look at another one. U.S. Department of Labor Statistics releases a monthly report on the average hourly wage of American employees. There was a recent sample of 500, there's N, sample of 500, and employees produced a mean hourly wage, that's my sample mean, isn't it, of $28.18 with a standard deviation. It doesn't say anything about population, so this is still talking about the sample mean, and it's the same sentence, it's the sample standard deviation, isn't it? $1.35, and so on. So we want the point estimate for the average hourly wage of American employees. Now, this one is going to have a degrees of freedom of 499. Now, I know that's really large. I could use the z-table with this one if I wanted to, or I could use that last row of the t-table. I think I'll go ahead and use the last row of the t-table just so we can look at what that looks like. So what's the confidence interval? They changed it on us. It's not one of the normal ones, is it? This time it's 98%. So be careful. We are used to doing the 99, 95, and 90. But 98%, I would say 1 minus 0.98, and that gives me alpha of 0.02. And when I divide that into, split it, it becomes 0.01. So now I've got to go look for my t-score, don't I? I have my degrees of freedom, which is so big, I know I'm only going to be using this last infinity row. And then what do I need? Well, I need my 0.01 is the area. Well, which column is 0.01? Here it is. So I'm going to use this middle, this third column, go down to the bottom, if I can show it to you, and I come up with a t-score of 2.3267. 2.3267 is what it is, right? Okay. So t-score 2.3267. Now, what's the standard deviation? I should have done that already. I take 1.35 and divide it by the square root of that big sample size, 500, and I come up with 0.0604. There's my standard deviation. So what do I know? Well, I know my margin of error is going to be this t-score of 2.3267 times my standard deviation that I adjusted, and that will give me my margin of error. Now I'm going to round this thing. It goes to a lot of decimal places, but I'm going to stop after 4. It goes 1405, and I'm really going to kind of round that to 0.14, go to 2 decimal places when I'm doing these confidence intervals. So now I'll take my point estimate, which was the sample mean. I'll say 28.18. Since it's money, we've rounded it to 2 decimal places. We'll say minus this 0.14 gives us a low number of 28.04, and a high number when I add is 28.32. Let's draw this so you'll see what it looks like on the curve. Of course, I'm dealing with t-scores, and I'm still dealing with sample means, and I've got the area that I'm interested in is new and different. It's 0.01 in each tail. which gave me my t-score of a negative 2.3267 and a positive 2.3267. And it gave me my confidence interval numbers. Here's the point estimate was 2818 in the middle, and the low number in my confidence interval is 2804, and the high number is 2832. So next example on page 12 is going to take us a little bit in a little different twist. It says the college would like to estimate the average number of hours students work per week. So they surveyed 15 students, there's my sample size, and they asked how many hours they worked, and here's the results. Now, that's all they've really given me. They didn't give me the sample mean, but they did give me the sample data. I can add those together and divide by the total number of students and get the sample mean. And they didn't give me the standard deviation, but they gave me the sample data. And I remember from chapter whatever, back there in chapter 2, I believe it was, don't we remember how to calculate the sample standard deviation from a group of data? We're going to put this into a list is what I'm going to do, and then I'm going to calculate it using one variable statistics. So let's take a look at my calculator, and I'm going to go to Stat and Edit, and I've already gone to save us time and put the data into List 2. I went to List 2 and I put all my data items there. I hope you can see that. Let me see if I can do a quick adjustment here to help us. There, that might make it better. So I put all of the data items into List 2, and now I go back to Stat again, and I go over to Calc, and I say one variable statistics, and I tell it to use List 2. And when it does that, it comes up with a sample mean of 16.8, and it gives me two standard deviations, a sample standard deviation and a population. Of course, I'm dealing with sample data, so I want the sample standard deviation. I'm going to go to 4 decimal places. I'm going to call it 11.7059. So get familiar with, if you don't remember how to do that, go back and refresh your memory on how to calculate the standard deviation and the sample mean from sample data. So that tells me what I need to know. The sample mean here is 16.8. I calculated it. I had a sample size of 15, so my degrees of freedom is 14. I have a standard deviation. I also used the calculator to find that. It's 11.7059. So I'm going to take it and divide it by the square root of that sample size, which is 15, right? And come up with a standard deviation that I can work with, 3.02. Now what's alpha? Well, they want a 90% confidence interval, don't they? So a 90% confidence interval for the mean is going to give me an alpha of 0.1 and an alpha divided by 2 of 0.05. That'll help me find my t-score. And so all I need is degrees of freedom in that area. I'm going to be looking on row 14 in my t-table. Row 14, and the area, the alpha divided by 2 area that I'm looking for is going to be right here, 0.05. So I'm going to go all the way down and across, and I come up with a t-score of 1.7613. So my margin of error takes that t-score and multiplies it times the adjusted standard deviation. And from here on, it's just exactly like we've been doing. The only difference here with this problem was we had to calculate the mean and the standard deviation, didn't we? And I'm going to come up with, let's see, this was 5.318 something. I've just rounded it. I went to, let's see, 5.32. I think you'll find that's what it rounds to anyway when you're going to just 2 decimal places with it. And now I'm going to take and say, okay, the point estimate 16.8 minus 5.32 gives me 11.48, and 16.8 plus 5.32 gives me 2212. What does that look like on the curve? Well, this is t and this is the sample mean. Sample mean that I calculated, 16.8, and then I built around this confidence interval. that had alpha divided by 2, and alpha divided by 2 was 0.05. So I split the alpha and put half in each tail. Came up with my t-score, negative 1.7613 and positive 1.7613. And then I subtracted my margin of error from the point estimate in the middle, and it was 11.48. Added my margin of error, and I got 2212. So I have a specific row. This row is t-scores, this row is data values. Now let's go to the next type of problem. We did look at means, and we looked at sample means, and now we're going to look at we're going to look at proportion problems. So with a proportion problem, we're always going to use the z-table, and that's the major thing you want to know. But what this is we call it the confidence interval for the population proportion, which is of course p, and we find that by starting with the sample proportion, p hat, adding and subtracting our margin of error, which is the z-score times the standard deviation of the p hat, the population proportion, the sample proportion of the sampling issue that we have. So we're going to call that, of course, that last part of it is called the margin of error, and we do the exact same thing that we've done before. We're going to estimate the standard deviation of p hat by saying p hat times q hat divided by n and taking the square root. Now this time, notice that what we're using to get this sample, the standard deviation of p hat, is we're using p hat times q hat. Before, what we were using is p times q divided by n. So this time, these are sampling proportions, the sample proportion data that we're going to be using, and you're just going to want to watch out for that. In these problems, you're going to have a population proportion given to you, and you're also going to have a sampling proportion, so you have to know which one you're using. Watch your formulas for this particular type of problem. So let's talk a little bit about population and sample proportions. Suppose that 80 out of 100 students in a very large class pass a test. Well, the percentage of students who pass the test is 80%. So the proportion of students who pass the test is 0.8 or 80%. Since this proportion involves the entire class, we would say this is the population proportion. It was all the students, and we would write it as P is equal to 0.8. Now what about this? 50 students at the college were asked if they planned to transfer to a 4-year degree program after earning their associate's degree. 35 of the students said yes, they are. So the percentage of students that plan to transfer after finishing for a 4-year degree is 35 out of 50. We divide that and then multiply it times 100, we come up with 70%. So that would be a proportion of 0.7. Now, since that data came from a sample that we took, it's not all the students at the college, it was only a sample that we took, we call this a sample proportion, and we write it as p hat is equal to 0.7. So each month, our example says, the Bureau of Labor Statistics estimates the national unemployment rate. The unemployment rate is defined as the percentage of the labor force that is not currently employed, but they could be employed. Suppose there was a recent survey found out that 54 out of the random sample of 1,500 Americans were jobless. So we know our sample proportion, don't we? 54 out of the 1,500, and this is our sample. So it's going to be our sample proportion, or p hat, isn't it? We're going to determine the point estimate for the proportion of all unemployed Americans, and we're going to determine the margin of error, and this time we're going to use a 97% confidence interval. That's one we haven't done before. So we're asked to construct a 97% confidence interval for the proportion of unemployed Americans. First, what's our sample size with this? Now, what they did was they surveyed, I have to read it because it's written in here, they surveyed a sample of 1,500. There's my sample size. And I need a z-score, don't I? I'm going to come up with a z-score for 97%. Well, what's alpha? 1 minus 0.97 gives me 0.03. I divide that by 2 and I have 0.015. So I have to go to the z-table and I have to look up on the negative side, right? 0.015. We haven't done this in a while, so let's do it. All proportion problems will always use the Z table, by the way. There's never a question of using T. So I'm going to look up 0.015. And I come up with, see if I can find it, 0.01, there it is. There it is, 0.015, found it exactly. And I come up with a Z-score of 2.17. I only need the positive, so I'm going to write it down, 2.17. Even though I look it up on the negative side, this requires me for calculations just to use the positive version. And then I'm going to say they're asking me for something called my sample proportion. Well, I did get a sample proportion. Out of the sample, 54 out of the 1,500 were jobless. So that's a proportion. 54 out of 1,500 were jobless. Okay, so what that comes out to be, once I do the division, 0.036. Now, if P hat is 0.036, Q hat is 1 minus 0.036, right? And that would be 0.964. Okay, so I've got that taken care of. What do I use as my standard deviation of P hat? Well, I use P hat and Q hat to calculate it. Under the radical, I say P hat, which is 0.036, times Q hat, which is 0.964, and I divide by the 1,500 sample size, and all of that is under the radical sign. I do this calculation, and I'm going to go to 6 decimal places with it, because these are proportion problems and they are laden down with decimal places, and I have it. Now, what's the point estimate for this population? Well, the point estimate is always going to be around the sample mean. Well, in this case, the sample proportion, right? So I'm going to say it's 0.036. There's my point estimate. And then I have to find the margin of error, don't I? Because I'm building a confidence interval. What is the margin of error? So the margin of error is always going to be the Z-score, which is 2.17, times the standard deviation that I calculated, 0.004810. And that comes up to be 0.0104. Okay, so I'll build this confidence interval, won't I? And here it is. I'm going to draw it. And it's a 97% confidence interval. It's using Z, and these are P hat values, aren't they? 0 is the center of Z, and the sample that I'm building around, the sample proportion, is 0.036. And I come over here and set up my alpha divided by 2 area. Since it was a 97%, this area is 0.015. This is just kind of showing you what we've already done. And when I looked up my Z-score, I came up with a negative 2.17 and a positive 2.17. And then I'm going to use that. I use that to calculate my margin of error. So I take 0.036 and I subtract the margin of error, 0.0104, and I come up with these numbers. Let's see, I can do it right here. I can write it for you. 0.036 plus and minus the margin of error, 0.0104. Confidence interval comes up to be 0.0256, and the high number, 0.0464. Basically the same thing we've been doing, right? The only real difference here is how we calculated that standard deviation and making sure that we were using P hat and Q hat and not P and Q. Sometimes you'll be given P and Q, so you have to watch for that. Okay, so what is it looking like in set notation? Well, it would just look like this with a comma between. And I could put it up here, 0.0256 equates to that Z-score, and 0.0464 is the one that matches up with that Z-score above. Now I'm doing all of this because I'm trying to help you with Chapter 9. Chapter 9, you're going to want to be able to see where the data values fall in relation to these Z-scores and T-scores so that you can finish up and do hypothesis testing. If I was looking at this as percentages, what would it look like? It would be 2.56%, wouldn't it? And 4.64%. Always be prepared to take your answers to either decimals or percents and pay attention to what they ask for. Now, page 14 has two estimates for population proportions that you should really be able to take the example that we just did and try on your own. So try those both and then come back and see if I can talk you through any problems that you might have had. All right, hopefully you're ready and you've had a chance to complete this work. Let's look at this first one. Each autumn, the consulting firm PwC surveys 2,000 Americans regarding their holiday spending plans. This year they found that 54% of the respondents plan to do the majority of their holiday shopping online. We want the point estimate for the proportion of all Americans that plan to do the majority of their shopping online. And we only have this sample that we're dealing with, 54% of the respondents to the survey. So this is really p-hat, isn't it? So 54% of the survey told us, but they want an estimate of the population proportion, which is the only reason we do confidence intervals anyway, is to get population, to look at what population data might be. So we're going to use a 90% confidence level for a 90% confidence interval, and we'll construct that for the statement here, the proportion of all Americans that plan to do the majority of their shopping online. Let's look at what it says. What's our sample size, first of all? Well, it said it surveyed 2,000 Americans. And then it said I want a 90% confidence level. Well, that's going to be 0.1, and alpha divided by 2 is 0.05, right? So I really know the 90% one. I'm not going to go back through that. We did that on page 3 if you want to go back through. Its z is 1.65. Here, I'll go ahead and put this down. The area I'm interested in, 0.05, in each tail of the curve. I can go ahead and start the chart. And this is z-scores again, because we're dealing with proportions. Now, the point estimate for that proportion is going to be the 54%, isn't it? 0.54. Now, if p-hat is 0.54, q-hat is 1 minus 0.54, or 0.46. But the point estimate is 0.54. It's always the sample proportion, isn't it? Just like it would be the sample mean in our other problems. So the standard deviation, well, we calculate that using p-hat times q-hat, and we divide by the sample size, which was large. Proportion sample sizes usually are very large. And we come up with 0.0111. So now I want to get my point estimate. Well, I said my point estimate's right here. It's 0.54, isn't it? And I want my margin of error. I'm going to take the z-score, 1.65, and multiply times the standard deviation that I just calculated. And it comes out to be 0.0183. So, I've got my z-scores here. I can go ahead and put them. So what equates to this place on my chart as far as the actual proportion data goes? Well, it would be the 0.54 minus 0.0183, right? And the 0.54 plus the 0.0183. I'm going to round that to 0.02. I'm going to call that really 0.02, okay? Make it a little easier for us, because this is hard enough when we're doing this to put these numbers in here. So what's the confidence interval? Well, really, it's going to go 0.54 minus 0.2 gives me 0.52. 0.54 plus 0.02 gives me 0.56. Or I could say that's 52% to 56%. Now, I'm 90% certain that between 52 and 56% of all Americans, plan to do their shopping online. The next example says there's a political campaign that wants to estimate the proportion of likely voters that plan to support their candidate. A campaign staffer selected a random sample of 30 and asked if they plan to vote for his candidate. The responses they gave are listed below. Well, there we go. Somebody gave us raw data instead of giving us actual proportions or actual sample means, right? So let's take a look at this one and see what we've actually got here. I want to determine the point estimate for the proportion of all yes voters. And then I'm going to do a 96% confidence interval for the proportion of all yes voters. So let's see if we can count the yeses and count the no's in this group. So I'm going to go through here and count, and you've done the same thing, and see how many I can find. So what I came up with is 19 yeses. Now, really, that's all I have to do, but I went through it just to make sure. I came up with 21 no's, and when I add them together, that comes out to 30. So I'm pretty sure I've got my yeses correct. So I know my sample proportion. My sample proportion is 19 out of 30 yeses, right? So it comes up to be 0.63. So my that would be p hat. My q hat would be actually represent the ones that voted no, and that's going to be 1 minus 0.63, which is 0.37. Now, how many do I have? Well, I took a sample of 30, didn't I? And I need a z-score associated with 96%. That's another one I haven't done before. So I say 0.1 minus 0.96, and I get 0.04, right? And I divide that by 2, and I've got 0.02. Now, I want to find the z-score associated with 0.02, and this is the way it looks if I draw it for you. This area is 0.02 on this side, and this area is 0.02 on this side, splitting alpha in two pieces. This is z's, and these are p hats. And the center of it, of course, is 0, and I do have my sample proportion now, so I can put it down here as my point estimate right there in the middle. So let's go and look on the negative side of our z-table and see if we find that area 0.02. As close as we're going to get to it, we're looking like 0.02 is going to give me a z of 2.0. I'm going to use this one, 5, okay? Could have used 5, could have used 6. I'm just going to choose that. 2.05, of course I just need the positive, don't I? So I'll say negative 2.05 would be here. Positive 2.05 would be here. The z-score I'll use in calculations is the positive 2.05. And then, lest I forget, let's go ahead and calculate the standard deviation using p hat and q hat and that sample size and taking the square root of everything. I get 0.088148. Okay, hopefully I'm agreeing with the numbers that you have already found. So I want to find the point estimate. I already found it. It's my sample proportion, 0.63. I want to find the margin of error at that 96% level. I'll use a z-score of 2.05, and multiply times the standard deviation, 0.088148, coming up with a margin of error of 0.1807. Now, I'm going to say my point estimate plus and minus 0.1807 is going to give me my confidence interval that I'm interested in. So I take 0.63 and I subtract 0.1807, and I get 0.4493. That's this number, the low limit. And then I take 0.63 and I add my margin of error, and I get 0.8107. So what do I look at this? If I want to look at it as percentages, it would be 44.93% to 81.07%. And what is it? Plan to vote for his candidate. And I'm 96% certain of that. Now let's take a little look real quick on page 15 of your guided notes and look at determining the sample size if we're estimating the population proportion. If we are given a certain confidence level and the standard deviation of the population, then the sample size is that's going to give us a predetermined margin of error for the confidence interval estimate for P is going to look like this. It's going to be the z-score squared times p hat times q hat divided by that margin of error squared. Remember our old, when we were looking at the sample size for estimating the mean, it was the z squared times the standard deviation squared. Well, instead of the standard deviation squared, we're using p hat times q hat to do this. So the value of p hat is usually gained by getting a preliminary set of sample data. But if no preliminary data is available, this is important. what we do is we use a most conservative estimate. Now that's really the worst case scenario for us, but the most conservative estimate of sample size means that you set both p hat and q hat to 0.5. So they're both equal, they're both 0.5, and that would give us the most conservative estimate for sample size. So let's look at this exercise on page 15. It says, suppose that the campaign staffer in our previous exercise knew about those issues before collecting any data for the confidence interval. So he wants to determine the most conservative estimate for the sample size required for a 96% confidence interval. And he wants that exercises the maximum margin of error allowed 2%. So he only wants a margin of error of 2%, but he wants a 96% confidence interval, and he wants to get the most conservative estimate of sample size. He doesn't know what his sample size is going to be, but he wants it to be his most conservative one. So he has to figure out sample size. We don't know. What is going to be our z-score, though? Well, that's going to be based on this 96%. Now, we already did this one before, and it came out to be, because we use those areas, it came out to be 2.05. So I'm going to go ahead and put 2.05. If you wonder how we get it, go back to page 14 and go over that again. Now, what is the p hat and q hat? Most conservative, I'm going to make them both 0.5. That's my most conservative sample size, okay? Now next, I need a place for my margin of error. So I'm going to come over here and say margin of error is equal to, and he gave me a 2%, 0.02. So that's one that I didn't give you a blank for, but go ahead and fill that in, okay? So what exactly is the sample size going to be? I'm going to use my formula at the top of this page here, and I'm going to say sample size is equal to the 2.05 squared that I had listed as my z-score times, remember, most conservative sample size, so I'm using p hat and q hat equal to each other, equal 0.5, and then my margin of error squared is down here on the bottom. When I do this calculation, I came out with 2626.56. It doesn't really matter because what I have to do is bump it up to the next person, right? And I come up with 2627. Now, if you've been given a sample proportion already that, preliminary data gave you a sample proportion, you'd use that instead of this p hat q hat equal to 0.5. Now, I've given you a little room to write your data here about precision of solutions, and you might want a chance to just kind of go back and summarize what you've learned in this chapter. But really what I want to tell you about this precision of solutions is this, let me get this out of the way for you, is that since chapter 6 we have looked at rounding errors, and we've seen that they can really affect the final solution of a probability calculation. For an example, when calculating probability, we see by hand, we round the z-scores to 2 decimal places and the t-scores to 4. And anytime one rounds to an intermediate step on a multi-step calculation, the final solution is always affected. It might just be a little bit. We're going to see the same issue happen with confidence intervals in Chapter 8. We're going to see it again with hypothesis test in Chapter 9. Now, if you have a graphing calculator, it's best to use that built-in functionality that calculates the confidence interval if you can, and that gets rid of the error that occurs from rounding. On the other hand, we don't really require a graphing calculator for this course, so if you're doing it by hand using those Z and T charts, which I'm doing, be sure you realize your solutions might be a tiny bit different than solutions that are found with a graphing calculator or any other software out there. If you're working with large data values, well, the difference could be quite pronounced. However, this doesn't mean a solution reached by hand is incorrect. So because of the variation of correct solutions to these types of questions, your homework and quiz exercises are coded to accept a range of possible solutions, and that gives us a tolerance either way, and that ensures that if you're using graphing calculator method or you're using the by hand method, you should still be okay. As far as the multiple choice tests are concerned, you understand the correct solution is going to be generated that is going to be equal to a graphing calculator solution, but a little rounding might take place. But you'll be able to tell your solution reached by hand. It might not be exactly the same, but it's going to be very, very, very close. It should be obvious which choice to select on a multiple choice question. And lastly, since homework and quiz exercises are going to give that range of solutions, sometimes this might allow solutions that are not quite correct to be scored as correct, and that might be a little confusing for you. For example, it's possible that a margin of error calculation is not correct, but scored got correct by the homework because it's close enough to the correct answer. But however, when the same incorrect margin of error is used to calculate a confidence interval, well, the confidence interval won't be close enough to the correct answer. So you're going to have to kind of watch what you do, and this means you have to be careful about your numbers and watch your decimal places, and just be aware of these possibilities. There's really no way around it, but as long as you're doing the calculations by hand, you'll be okay. As long as if you're using a graphing calculator, you should also be okay. But if you have any questions about whether your solution is correct or not being graded correct, let me know and I'll look into it. And occasionally one of these homework or quiz questions, that's coded might need to be tweaked just a little bit. So that's kind of what I wanted to tell you about that precision of solutions, and you might want to make some notes so that you can ask questions later, so that you can just remember as you're going through homework for chapters 8 and chapter 9.